I'm Mark Ahlstrom, President of the Board of Directors of the Energy Systems Integration Group, ESIG, and I welcome you to our monthly webinar for October. ESIG is a membership-based nonprofit organization providing objective information, resources, and networking in support of the energy transition. We do this through workshops, tutorials, webinars, blogs, working groups, and task force activities, and producing technical resource materials, as well as providing simplified briefing documents for decision makers who increasingly need to understand these complex technical issues. ESIG also serves in a leadership role for the Global Power System Transformation Consortium, often called GPST, whose mission is to bring together key actors to catalyze a rapid, clean global energy transition at unprecedented scope and speed. We've had a very busy year with our task forces and webinars, and we're looking forward to our fall technical workshop in San Diego next week. We have another great lineup of tutorials and technical sessions out there, and I hope to see you all there. There's always room for more if you want to show up there. It starts Monday morning in San Diego. Further information can be found on our esig.energy website, where the final agenda and registration link are available. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime on the ESIG website. Also check out joining ESIG as a member, which is quite inexpensive and gives everyone in your organization the access and participation in our working groups and task forces. You can find us on the web at www.esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. Just a few logistical matters before we get started. Attendees are muted for the webinar to avoid distractions. So for the Q&A, we're using the Slido platform. To ask your questions, please go to slido.com, S-L-I-D-O.com, and enter ESIG17 as the event code. You can also see that at the bottom of the title slide below. Of course, at Slido, you'll see a thumbs up button you can use to vote on questions that you want to prioritize, and we'll answer as many questions as we can in the Q&A time, focusing on the higher rated ones. We plan to save about 10 minutes for Q&A at the end, and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted, so you can see that later or share that with friends. We also plan to provide short responses to unanswered questions that we don't get to, so please don't be afraid to ask your questions through Slido, and you'll be getting all the answers and information. Today's topic is going to be Power to X, which is the generalized concept for using carbon-free electricity to produce other things like hydrogen, ammonia, and synthetic fuels. This is a topic of increasing interest and importance, with a great deal of attention around the world being focused on fully decarbonizing the electricity system, as well as difficult sectors like steel and cement. And here to talk about it with us today is Andrew Reimers, Director of Regulatory Affairs for Lancium, a startup specializing in demand management for large electrical loads. Andrew has previously worked as an electricity market analyst for the National Renewable Energy Lab, the Electric Reliability Council of Texas, and RWE Renewables. Lancium is a valued member of ESIG, and it's my great pleasure to welcome Andrew here today. So just one more reminder, use Slido, slido.com with event code ESIG17 to ask your questions. And Andrew, I'll turn it over to you.
Hello, everybody. Thank you for having me today, and thank you, Mark, for the introductions. Let's just jump into it. So I'll start with a little more of a description of what Power to X even is, and then I will sort of give my take on how it fits into the energy transition and the balancing of intermittent renewables. And then I want to discuss some of the challenges I see for how it could affect grid reliability, and then more of the economic functioning of the grid or planning functions of the grid, such as load forecasting, resource adequacy, and market design. And so without further ado, as Mark said in the introduction, Power to X is really a simple concept where we're taking electricity and we're using it to make other things. So probably the most common example you will hear is green hydrogen. That's really straightforward because hydrogen is a pretty major component of hydrocarbons, and hydrocarbons are one of the main inputs to everything about modern life. And so if we could figure out a way to produce those hydrocarbons through a electrical process, and we already have a pretty good sense of how to decarbonize the power system that can more rapidly decarbonize the economy overall than maybe having to find other ways of decarbonizing those processes. All that said, if we were actually to get all of that material through electrical processes, that would entail a large increase in the demand for electricity. So there's an aggregate increase in the amount of electricity we'd be consuming. And then in addition to that, there is the potential for even higher degrees of volatility or reliability issues with these loads potentially ramping up and down or tripping offline, things like that. All of that said, if these loads can be operated in a flexible or controllable way, they can play a big role in allowing greater adoption of intermittent renewables. And so there is a pro to the con of the reliability impact they pose. And for context, I'm going to present some of the analysis that's been presented in ERCOT's Large Flexible Load Task Force. Most of that deals with data centers and things like that, but I think that experience is really useful for providing some insights into how the power to X concept will play out over time. So, energy transition need for flexible resources. We've all seen charts like this. The grid, particularly heavily renewable grids like ERCOT, getting more and more of their generation from intermittent renewables. That means we need a lot more flexibility from our old thermal fleet. It also means that we need other forms of flexibility. So we're getting an increasing amount of that flexibility from storage. ERCOT has several thousand megawatts of storage and is expected to have twice as much at this time next year. We could also get more of that flexibility from transmission, which is sort of a way to balance out intermittency over geographies where it might not be sunny or windy everywhere, but it is sunny or windy somewhere a lot of the time. And then we can increasingly get more of this flexibility from the demand side of the equation. And this is the small plug for my company that we are still the only controllable load operator in the market that is not strictly a battery management business. So the question is, how flexible are these power to X loads? Like, can they actually be used to balance the intermittency of renewables? And that really depends on what specifically you're talking about. So for example, hydrogen electrolysis does appear to be a pretty flexible process. You're applying a current to an electrolyzer. You can turn that up and down. They seem to be able to be pretty responsive to ramping and even things like frequency response and stuff like that. However, ammonia synthesis for green ammonia, there's still a thermochemical aspect to that where it's not likely to be as flexible as green hydrogen. So putting this just a little more technically, only a subset of these loads are likely to be able to follow base points or dispatch instructions from the grid, or to be able to follow frequency response and things like that. However, a subset of these loads can probably respond to somewhat longer timescale instructions. So for example, a load might not be able to ramp up and down every 5 minutes, but it might be able to receive an instruction to be turned down 30 minutes or an hour from now. So one example of something that could do that in a more market-oriented process would be like a multi-interval sched. It could also be through something like DAM, where loads kind of get a schedule for when they are able to operate most cost effectively. Right now, there is a process for being a controllable load in ERCOT where you submit a bid to buy curve and get dispatch instructions from the grid. But one of the main bottlenecks to doing that is that loads are still required to be able to provide primary frequency response. That means when there is a frequency change on the grid, loads have to be able to drop their load in response to that frequency event and in proportion to that frequency event. And this really limits the extent to which a lot of loads either are physically able to be controllable loads, or whether they would even want to. So if you think about certain kinds of data centers, they might be able to adjust their output every 5 minutes according to base points, but they don't really want to drop their load out of nowhere due to some kind of acute frequency situation. And so there's proposals out there to have separate categories of controllable loads, some of which that are frequency responsive and some aren't. And that gets into trade-offs between perceived reliability issues versus kind of market efficiency, controllability benefits. There's also a question of, if you have a big P2X plant, some of those processes might be frequency responsive and some might not. And just to add some illustration to all of this, this is an example of a green ammonia facility. A green ammonia facility is essentially a green hydrogen facility in parallel with a ammonia synthesis plant. And so, as I've stated before, the electrolysis portion of this plant can likely be pretty frequency responsive and flexible. And so on one hand, this is just taking electricity, producing hydrogen. We'll explain more about what the storage is used for. That can go into other feedstocks, or it can go into this ammonia synthesis reaction. On the other side of the ledger here, we have an air separation unit pulling the nitrogen out of the air. That nitrogen reacts with the hydrogen to produce ammonia. As I stated before, this is really a thermochemical process. It has to get up to a pretty high temperature before it starts running. And so you really don't want to be choking this off and have to continually be restarting it. And so in the event that you were trying to respond to a frequency event or price response or something like that, you would really only want to turn off the electrolysis plant. You might even want some storage for the nitrogen here, because you want to have hydrogen storage in reserve to keep feeding this ammonia process while the electrolysis plant is turned down. And so this is just an example of how different processes within a P2X plant might have different degrees of flexibility, and that needs to be taken into account both from the operator perspective, but also from the grid's perspective. So that was just a brief description of how the flexibility of these loads might be applicable for various grid operational challenges, but there are a lot of other challenges these loads pose. In particular, most of our kind of grid reliability paradigm is based on maintaining enough generation to meet supply, meaning most of our kind of reserve projects or contingency forecasts and things like that are based on, what if power plants are out and we need to spin up another power plant, or we need to keep energy in reserve for the event that a generation is out or something like that. The power to X concept really flips that on its head and emphasizes a bunch of problems where, what happens if load drops really quickly? And so load could drop really quickly, either A, because it's just ramping, either as a normal part of its operation, or because it is trying to be price responsive. So if it is really exposed to real-time prices, and then you have a really high real-time price, that load's going to try to avoid that, and it could ramp really quickly. Or there could be a voltage instability event on the grid. The voltage drops generally, and the equipment is designed to shut the system off to protect the equipment, because it's not meant to operate under those low voltage conditions. Well, if that happens, now the load on the system has just decreased, and the system frequency goes up. It changes the power flow on the system, which could cause transmission overloads, all kinds of instability and reliability events that our current kind of ancillary service suite is not really well suited to deal with. And so what can grid operators really do to manage this situation. Some sets of loads, they can probably just impose ramp rate restrictions or voltage ride-through requirements on. But particularly for the ramp rate restrictions, there are some loads where that's just not physically feasible. So for example, steel arc furnaces, that is just a load that ramps pretty substantially as a matter of its normal operating, parameters. It also might not be legal, frankly, for ISOs to impose these kind of restrictions on loads that are not, certain types of resources or whatever. So it's one thing if a load is a registered resource that's meant to be providing services to the grid, they might have a certain set of characteristics they're supposed to maintain. But for all other loads, it's really unclear what the grid can actually force them to be able to do in terms of ramping or voltage ride through. Alternatively, the grid could just procure more regulation down or revise how primary frequency response works in terms of over frequency events rather than just under frequency events. And with regard to voltage ride through, there are a lot of things that can be done to improve voltage stability throughout the grid, whether that's having more generators that are able to provide reactive power and voltage support, or revising the transmission planning process to have more capacitance in different parts of the grid. But as is always the case, the question is how much and who pays for it. And it seems to be a totally valid question whether the loads that are, whether whoever is causing the voltage stability issues should be responsible for fixing them. So, okay, so there we go. I am actually using a slide that I boosted from Evan Neal, who I think is on the call today, and it appears to still have his animations in it. So that is a fun surprise. So what this slide is showing is this is data from the Large Flexible Load Task Force, where we're showing for the month of August, the blue lines are the amount of regulation procured on an hourly basis. So the top of these charts is regulation up, corresponding to the ramp up on average of all of the large flexible loads in ERCOT. So these are loads that have gone through a certain process and are designated as large flexible loads. Similarly, the bottom chart is reg down and down ramp of large flexible loads. Let's get the text here. And what this chart is showing is that there are already a lot of intervals where ramp up is exceeding up ramp regulation and ramp down is exceeding down regulation. So if you look on the top chart near the right of the chart, you have a lot of situations where the large flexible loads are ramping faster than up regulation is able to respond to. And similarly, in the middle of the day, we're having a lot of situations where down ramp is happening faster than the down regulation is able to respond to. And this problem is only likely to get worse as more loads like this energize, leading to reliability issues if they continue to exhaust regulation beyond what ERCOT procures. Similarly, another slide from ERCOT, this one's from Jeff Billow, showing load loss events due to voltage instability issues. The largest of these being this 1600 megawatt event in West Texas, where a voltage drop on the system caused some 1600 megawatts of load to drop off. And so that caused a frequency spike. And this is only 1600 megawatts. And we're talking about much, much more capacity on the system that could be susceptible to these kinds of events. And so that is the real concern, is that if we don't get if system operators don't get a grip on these kinds of issues, the reliability issues are just going to get a lot worse. And they're going to get worse even more so because of the scale of the projects people are building. And so if you look at the kind of projects that are being proposed, the scale of these projects is really impressive. So there's a lot of reasons that project developers want to build bigger facilities. So if we're talking specifically about power to X, there are all sorts of balance of plant issues that benefit from the economies of scale, whether that's transformers or transmission stuff or water connections or what have you. Data centers, there's actual physical reasons why they benefit from having more load all in one kind of tight package. The bigger they are, though, the more of a reliability issue they pose if they are to drop off for some reason. So not only is the aggregate amount of these projects going up, but the size of each individual project is, a lot of them are very, very large. And I am going to show you just some announced projects so you can get a sense for the scale here. There's a green hydrogen project in South Texas that's been announced that's just under 2 gigawatts. A similar project in Australia is twice that big. There's a whole complex of green hydrogen projects scheduled, announced, forecasted for the Netherlands. The first few of these are a few gigawatts each. Probably the most, we could say, ambitious or audacious, depending on your perspective, project I've seen is this Hydrogen City project in South Texas, where it's supposed to be somewhere on the order of 60 gigawatts when it's all said and done. For reference, the peak demand record in ERCOT is around 85 gigawatts. So this is a truly mammoth project vision. And so the reliability issue is very significant, particularly because of how big some of these facilities are. And it's going to take a lot of kind of creative thinking about how to deal with all of that as far as maintaining the reliability of the grid. Moving on to more like economic and planning related issues, load forecasting, resource adequacy, and market design. One of the challenges with load forecasting for these types of loads is it's really hard to know what their operating economics are. So if you think about power generation, it has, it takes in fuel to produce electricity. Well, if you flip that around and you take electricity to produce all sorts of other things, whether or not it is valuable for that facility to be running depends on the cost of those other things. And power system operators are really ill-equipped to be tracking the spot prices of all sorts of different chemical commodities. They don't really have an insight into what these different facilities, what the spot price of hydrogen is on a given day, what the spot price is of ammonia on a given day. And even if they did, different projects have kind of different operational paradigms for dealing with that kind of stuff. They might have fixed contracts for electricity. They might have fixed deliveries, so they can't really ramp up and down super related to the price on the wholesale market because they have customers and deliveries that they have to make. If you think back to that green ammonia slide I had at the top, it's totally feasible that you could have a project that can adjust its output of hydrogen and ammonia depending on the relative price of those things. And those are all complications that system operators are going to have a better view into if they're going to forecast what the load is likely to be on any given day. And so I have one more figure here, again from Evan Neal at ERCOT, showing the price responsiveness of the large flexible loads in ERCOT. And you can see over on the right of this slide, several of these loads are extremely price responsive. So based on ERCOT's view of what the kind of break-even price is for these projects, some of these loads are always curtailing when the price of electricity gets above that point. On the opposite end, you have a lot of loads that are hardly price responsive at all. And regardless of what the price is, they continue to run. And so not only does a system like ERCOT need to know what that break-even price is, but characterizing which projects tend to be more or less responsive to the price signal goes a long way to your figuring out your ultimate load forecast. This is sort of a illustration of how complicated this can be. So this is an example of how the break-even price for different products manifests itself as a bid to buy curve for these different projects. So we're using this related to that green ammonia project schematic I had above. I have on the left just some made up economic inputs for this. So the energy intensity of green ammonia is something like 11 megawatt hours per ton of ammonia. And for hydrogen, it's something like 53 megawatt hours per ton of hydrogen. And then if you take a assumed spot price for either of these commodities, you can calculate a break-even price. So if ammonia is $1,000 a ton, that corresponds to a break-even price of $90 a megawatt hour. If it is $300 a ton, that corresponds to a break-even price of $27 a megawatt hour. Similarly, if hydrogen is $3,000 a ton, you get a break-even price of $56 a megawatt hour. How does that translate into a bid to buy curve for a controllable load? And for those who are unfamiliar with the concept, a bid to buy curve is basically, here's how much I am going to pay to buy this much electricity. And the idea here being whatever I am producing with the electricity is worth at least this much. And this is sort of my indifference point at which above this price, the electricity is no longer worth buying because it would cost more than the value I get from whatever I'm going to produce. Okay. So on the left, the idea here is, imagine this is a facility that is just going to orient all of its operation around whichever of the commodities is worth more on any given day. And so if the price of ammonia is $1,000 a ton, that is worth more than the hydrogen. And so all 100% of this facility is buying electricity and has a break-even price of $90. If it's only $300 a ton for ammonia, the hydrogen's worth more. And so now the facility is reoriented around producing hydrogen and the break-even price is $56 a megawatt hour. That means if the price for electricity in the middle of the day is higher than $56 a megawatt hour, this facility is less likely to be running at all. And so that impacts the load forecast for that facility. Similarly, if you have a facility that kind of generally operates at an 80-20 volume split, you can see how the same math impact its bid to buy curve, where 80% of the facility is dedicated to producing ammonia. In the lower example, that means 80% of this facility isn't really economical to run if the price gets above $27 a megawatt hour. And so for much of the year, that would not be economical to do. So this is just an illustration for how these kind of commodity break-even price economics would influence a load forecast. One other kind of market design thing to think about is locational marginal pricing. In general, the idea has been CLRs should get nodal pricing because that'll incentivize them to locate where prices are lower. And in general, that makes a lot of sense, but there are a lot of challenges to that. The obvious being, if you're producing something massive, data centers, they don't produce anything that has to be trucked around long distances, but if you're producing hydrogen or ammonia, going out to where the low electricity prices are also means going further away from customers, and transportation can be a substantial component of getting these products to market. And so there's a pretty big trade-off between the cost of electricity and the cost of transportation. More subtly, the issue is these low electricity price regions are also where you're most likely to have voltage stability or congestion issues. And so that's kind of an issue that isn't necessarily accounted for in the nodal pricing construct, that these are areas that could entail more expensive transmission upgrades or something like that, or could cause more of a reliability issue if a bunch of loads start siting out there. Even so, these places look like they have low prices based on historical data, but a lot of them don't have the transfer capacity to build tens of megawatts even necessarily. And so they would need a lot of new transmission upgrades in the first place. And so there's a pretty big transmission planning component to all of this. And then a more fundamentally complicating factor here is that, particularly through the middle of the country here in SPP and MISO, a lot of these regions are in regulated retail territories. And the main problem with all that is that you can't really benefit from being a flexible load if you're in a regulated retail territory where you're getting a fixed rate. And so a lot of these areas are really not either able to or incentivized to offer rates that are indexed to the fundamental wholesale price. And so that's really going to limit how much loads like this are able to make their economics work through the middle of the country. So another way to kind of summarize all of that is that flexible loads really monetize their flexibility the most when they're in a competitive wholesale market and competitive retail market, where they have some exposure to the wholesale prices and can be price responsive, and then can earn revenue from providing ancillary services. Lastly, I want to talk about resource adequacy and how I see the conventional resource adequacy methodology being pretty ill-equipped to deal with a problem like this. So resource adequacy will look at, so there's the short-term problem that is less complicated. You look at projects that are in the queue, you look at maybe demand projects that are in the queue, you run some analysis and see if you're going to have enough energy to cover all of that demand. Now, that might still not show the whole picture because it's unclear whether certain projects will be running during, say, peak demand conditions. So if these green hydrogen projects, these green ammonia projects have a break-even price of $90 a megawatt hour, they're not really likely to be running when the price of electricity is $1,000 a megawatt hour, which is really what resource adequacy modeling is trying to look at, is those times of really acute scarcity. An even more complicated problem, though, is looking out further into the future, where you go beyond kind of the horizon of how much capacity has already gone through the planning process, and you're trying to figure out what's the equilibrium capacity based on how much revenue is going to be in the market. And for that kind of analysis, much of the demand side of the equation is treated as exogenous. So you have, when I was at RWE, for example, we would plug in the price of hydrogen. And if we didn't put a cap on the price of hydrogen, it would build tons of electrolysis load, because $3,000 a ton is actually a pretty healthy price for building a lot of electrolysis. And so you couldn't really do that. You kind of had to tweak it and put in a bunch of made up exogenous inputs, when the way I see it, the more appropriate way to do this is to recognize that there is a kind of recursive feedback loop here, where there's an equilibrium where you have enough generation to meet a certain amount of P2X load, where the price of electricity is essentially the intersection between those two things. And I don't think that the current planning paradigm really accounts for anything like that. And I'll just give one particular example that I think is interesting, is if you think of something like effective load carrying capacity, that's going to be heavily influenced by how these P2X loads site themselves. So if these P2X loads are siting in and around areas that have a lot of stranded wind assets, those wind assets' effective load carrying capacity is going to go up, where today the marginal ELCC for a wind project in the Panhandle in Texas is pretty close to zero. If you were to start building a lot of these loads out there, it would potentially be non-zero. And so that is just one example for how the siting decisions for these loads can really impact your resource adequacy methodology. And more abstractly, our view on future resource adequacy is also recursive as far as how we design our markets. And so we're constantly revising our capacity markets or our scarcity pricing mechanisms or what have you because of perceived risk of scarcity in the future. And so if we see a future, like the E3 report in Texas got a lot of attention based on the view that a ton of capacity was going to be leaving the market and so on and so forth, and that would result in a certain loss of load expectation. Well, if you're not if you're not accounting for all of these different equilibrium issues in that methodology, you're going to get the wrong conclusions from those results and make market design changes based on those results that may or may not actually be appropriate. And so I am making the case that there needs to be a more thorough equilibrium oriented analysis for figuring out how much of this kind of load is likely to materialize based on how the different economics of generation and load kind of play out. So that is all I have, and that took 37 minutes, so that is plenty of time for questions. So just to reiterate, I am making the case that Power-to-X, while it has a lot of upside as far as allowing us to integrate more intermittent renewables into the system, it also poses some physical and economic challenges for the grid. And in particular, we need to consider new methodologies for dealing with a lot of these problems, whether it's load forecasting, resource adequacy, transmission planning, et cetera. So with that, I will.
Andrew.
Yep.
No, fascinating. Well, I'm hosting, so I'm going to ask the first question, actually. We talk a lot about ERCOT with this, and you can actually kind of treat large loads as wholesale market participants in ERCOT, right? And you can kind of even combine them with other generation through a private use network or other things that ERCOT does. How specific is that to the ERCOT market in Texas? And have you looked at like MISO SPP, for example, that are also, great resource, a lot of interest, but can you do that same sort of thing there, and how would you do it?
We've looked at it more with PJM, the problem with MISO and SPP being the retail side of the problem. So you really have to make particular arrangements with the retailer, with your utility in an area like MISO and SPP, where there's a lot more opportunity in a more deregulated environment like PJM. And it is different, but it does appear that PJM is another area that you could monetize this kind of flexibility.
Right, because the retail side is deregulated as well, right?
That's right.
Yeah, and in a lot of the other parts of the country, under state law, the loads would drop down to the local utility or co-op, right?
That's right.
Work with them. Okay.
You have to work with them, and then those utilities, if they're investor-owned utilities, they have to file a rate case to offer you anything new. And so then it becomes a whole thing about, are the public utilities commissions of these states able to kind of allow rate plans that make any sense for this kind of arrangement? And legally, it's not always clear, because can they offer a rate that is just a function of the wholesale rate, or do they have to publish the rate in advance, for example?
Yeah, there's lots of interesting issues here, and some of them don't fully even allow loads to be exposed to the real-time spot price, right?
That's
There's an average price of
zonal price. Intentional that the prices that they offer are meant to be kind of a blended cost recovery price, rather than giving a particular project a price that reflects its cost. In some states, it is regulated practically all the way up. And so if you look at Iowa in MISO, I've done a lot of work looking at that. And you start at the distribution co-op level, and they have to buy from the generation and transmission co-op, and they have to buy from Mid-American. And then only once you get all the way up to Mid-American does anybody have any market exposure. And so the value of the flexibility is just obscured by multiple layers of regulation there.
Yeah, I think it's a real game changer for the industry because it's really going to shake up how we view this, to view loads as essentially what you'd like to do is make them market participants, just like a
That's right.
generator in a sense. Right. Related to that, though, I mean, sometimes if we can't, the first question here is, what's your view on larger renewable plants that are off grid and built specifically for producing green hydrogen? And I know we don't even have the detailed rules from the IRS about exactly what qualifies as green just yet, but we are seeing some stuff like ammonia plants that have a dedicated wind plant already, things like that.
I have two thoughts. One is the capital amortization is going to be challenging because if you build a wind plant that either it's oversized for the load, in which case you have stranded electricity, or they're right sized for each other and the load is getting a capacity factor of at best say 40%, and that is just a really low uptime for a capitally intensive project. And so if you're grid connected, even if you're following these break-even economics, it's a lot easier to get uptimes that higher uptimes and relatively low prices. I mean, I've done the analysis in Texas, and if you were in West Texas and only running on the lowest 80% of hours or something, 70% of hours, you can get a levelized cost of hydrogen lower than $3 a kilogram, which means even if you were giving away the hydrogen, the production tax credit would be more than enough to recover your costs. And so that is a very big benefit relative to getting a 5 cent a kilowatt hour fixed price from a regulated utility, and that would be a very good price.
Right. Yeah, clearly there's a lot of advantages of staying grid connected for the grid as well, I think.
I agree.
Yeah, but you have to be able to get through the interconnection queue in some of the regions, so there's other issues. Right?
Yes, for sure. And I didn't get into that in detail because I think it's a pretty well explored topic, but I will say adding gigawatts of load to our already overwhelmed interconnection process is only going to throw further fuel on the fire that those processes need to be reformed somehow.
Agreed. Yeah, thanks. You mentioned PJM a bit. How should regions with capacity markets or regulated resource adequacy planning think about RA accreditation with regard to these sort of projects? How do you avoid redundant RA procurement to cover these loads?
Right. And that is an excellent question. And the way I think about it is you really need to determine kind of the ELCCs and RA requirements of these loads using kind of a production cost methodology. So you have some sense of what these projects break even price is, and then you're doing some kind of simulation about peak load conditions and things like that, and evaluating whether these loads are likely to be on in the first place. And so if it's something like an AI data center that has a value of lost load of $20,000 a megawatt hour, then it should be more susceptible to capacity payments than a green hydrogen project that in all likelihood is going to have a break-even price below $100 per megawatt hour.
Mm-hmm.
I'm a big advocate for using production cost methodology more widely for this type of planning. It's just different types of analyses have different both temporal and geographic specificity that's needed to do it right.
Yeah, it seems inevitable we're moving toward more of that sort of fidelity of production cost type approaches. Operating assumptions that you should be studied for, and then probably also study for the interconnection upgrades as well, I would say.
Yeah.
But that's a whole other topic. Yeah. And I want to assure people I did not ask, nor did I vote on this question, is it mentioning hybrids. So given the potential benefit of incorporating willingness to pay based demand bids into energy market pricing, are there RTOs incorporating? No, it's moving around. Given the potential benefits of co-locating variable renewable energy with power to X resources, how are or should market operators think about hybrid VRE plus load resources? Is there a benefit of actually combining them at the single point of interconnection and do some behind the POI stuff here? Or do you see the market as
I'm a little,
significantly?
I'll just say that I'm skeptical. The main benefit I kind of see is better utilization of substations and things like that. So if you can design the substations in such a way that uh, load and generation can share the transformers and everything, that is a pretty big bottleneck in the kind of EPC aspect of building all of this stuff today. But from a
Yeah,
market operations standpoint, I am actually pretty skeptical of this and think that the synchronized bulk power system is the thing and not making these islanded private use networks. Now we might need some of those because some of these loads want to keep running through voltage stability issues and things like that, or
mhm,
they are so big that if we don't have redundant generation directly connected to them, they pose so much of a reliability risk that they're going to have their own generation on site. You know, this 60 gigawatt hydrogen city thing only even makes sense in a context where it has a lot of its own generation,
right.
because
Yeah,
otherwise it could crash the whole grid. So there are certain situations, data centers are another one. I think it isn't really the topic of today's conversation, but if you look at some of the AI data centers that are being proposed, they're hundreds of megawatts. I think
right,
they will be increasingly scrutinized for what exactly they have on site as far as backup power generation.
right. Makes sense. Yeah, and also not so much in ERCOT maybe, but in other markets where the interconnection upgrade costs are substantial sometimes.
Yeah.
I can see benefits of, for
Yes.
your particular scenario, you want to minimize your injection limit that you have to pay for, right?
Yep. Yep. That part I
So
totally see.
yeah,
If you're talking
very good.
about the cost of interconnection, the cost of poles and wires and transformers and things like that, or even just
Right,
speeding up the interconnection process, I can see an argument for that.
right. Makes sense. Okay. Uh, let's see. Are there any RTOs, ISOs incorporating willingness to pay based demand bids into energy market pricing? Now, sounds like we need a demand curve.
Yeah, it's not quite like that, but I know that a lot of, and I don't know if the person who explained this to me is on here. I know there is, so FERC 2222 has a lot of, has resulted in markets developing this net benefits test and having some economic benefits for loads for curtailing under certain circumstances. Uh,
Hmm.
it is not quite the same thing as what you suggested, where you submit a bid to buy curve and then are dispatched according to the grid, but it is approximating something like that, I'll say. But that is the closest thing I've seen, is that PJM, MISO, SPP have a kind of demand response price that loads can respond to.
Yeah, yeah. And I would add, if the markets really do fully implement 2222, I think there's some interesting implications from that that could be applied more generally in the markets like this. Yeah, very interesting. Um, let's see. In demand for power to, if demand for power to X operates only when prices are low enough, why would resource adequacy results change for renewables? I guess you're using a West Texas
Oh
example
yeah, that
of,
is well, it would increase the amount of renewables that could economically be built because they wouldn't be being curtailed as often.
yeah, so it's really based on transmission
Yeah,
availability and deliverability from the renewables to these loads, right?
right. I think that
If you're in a
that
curtailed area. Okay, interesting. Yeah, makes sense. Um, and this is kind of related. You mentioned Texas, that do existing large flexible loads in ERCOT submit formal bid to buy curves to ERCOT, or do they independently curtail in response to price?
the only ones submitting formal bid to buy curves are the ones operated by Lancium, uh,
Okay.
and the rest of them are informally price responsive. And
Okay.
just to add a little color to that, there's still a benefit from being formally in the SCAD optimization process because you're no longer reacting to prices as much as you're part of the optimization itself. And so you're automatically being turned down when a new price prints, as opposed to having to kind of react to pricing events.
Okay. So there are advantages, I think, for sure. Okay. Um, we talked about this a little bit, but there was a high-rated question here too. Who has jurisdiction over large load interconnection? Solely the RTO, ISO, distribution utility, who determines what grid upgrades are needed for a big load?
It's
Uh,
both. Yeah. So the
yeah.
transmission distribution utility is usually the first uh, gatekeeper, and then it goes up to the system operator after that.
Okay. Yeah. To deal with the interconnection process.
That's right. And they will also make a lot of the uh, decisions about what transmission, or at least make the case about what kind of transmission upgrades are needed.
And would those transmission upgrade costs, I mean, you talked about it, is it legal to pass those through to loads and have them pay to interconnect as a load?
That's my understanding.
Okay. Uh, yeah, what are your thoughts on the relationship between power to X flexible loads and transmission cost allocation structures such as the 4CP in ERCOT?
Ooh, yeah, interesting.
There we're in deep. Okay.
Yeah, no, that's a great question. I think I share the IMM's general critique of 4CP in that it is a pretty kludgy out of market uh, transmission cost allocation methodology that doesn't really work anymore. And I do think that loads like this would be likely to avoid it and then therefore not pay uh, for whatever part of the transmission cost allocation is paid for by 4CP. And so I think there are a variety of different transmission cost allocation methodologies that would probably have better results.
Okay, thank you. Uh, we got several here more. Good, let's see. We just mentioned transmission upgrades. I'm just going to want to take that one. Do you foresee a significant amount of additional transmission upgrades required above beyond business as usual to successfully integrate power to X at wide scale?
It is a possible solution. I don't know how we get from here to there because the transmission planning criteria are what they are as far as the cases that have to be made to justify rate basing transmission upgrades and things like that. So I kind of think it would need to be the transmission planning criteria would need to be changed to make it fully account for the reliability issues posed by projects like this. And then you would get a lot more upgrades probably. Either you would get more upgrades or it would you would end up having other impositions that just reduce the likelihood of these kind of projects being built in the first place. So for example, if they have to have certain voltage ride-through criteria, but you don't have a transmission planning process that is going to prevent the voltage instability problems in the first place, well then it becomes a lot harder to build a project that is likely to be tripping and violating compliance.
Yeah, it seems to be part of a bigger issue about do we get transmission planning to really take all this into account in a robust way, or do you do this on essentially paid for by projects, by
Mhm.
generators and loads, right?
Right.
It's all part of that debate.
Well,
Okay.
and there is I do think it is not a straightforward question to figure out how to divvy up these costs. You know,
Yeah.
if these voltage stability issues really are being caused by loads out in the less developed parts of the grid, then maybe they should have to pay for the upgrades. But that's a really hard thing to determine. And then there's also just an ongoing conversation about how much of these voltage stability issues are caused by, you know, inverter-based resources, for example. And so assigning blame is not straightforward. And so allocating costs isn't either.
Right, right. Uh, related, let's see, this question, well, it really, the question here, it mentions voltage frequency stability. With the issues you mentioned about load ramping up and down and frequency voltage stability be mitigated if markets were closer to 5 minutes or faster rather than hourly? I mean, aren't we
Well,
talking about actually using the 5-minute dispatch in ERCOT,
yeah,
for example?
yeah.
Or
So
okay,
dispatch instructions are every 5 minutes in ERCOT.
yeah,
And the issues we're talking about are on quicker timescales than that. So regulation, for example, in ERCOT is every 4 seconds. And
right,
so if you were following base points, you're not really part of the problem, because the way it works in ERCOT, for example, if I get an instruction to curtail my load, I am given updated instructions of where I'm supposed to be every 4 seconds. And so as long as I'm following that instruction, somewhere else on the other side of the equation, load and demand or demand and supply are in balance with each other. It's the out of sked ramping that is being balanced by regulation, and that new signals are sent to whoever's providing the regulation every 4 seconds. But it's not uncommon for that regulation to be totally exhausted. So then there's no other units to turn up according to like the balance supply and demand.
yeah. But the more you can get these units actually participating in the sked and be dispatched every,
Yeah.
at least every
So
five
for
minutes,
the
the better, right?
units who
Yeah.
can follow base points and don't inherently have big swings in their load, that is
Mhm.
a solution. Uh, I just see several types of load where, whether it's certain kinds of data centers or steel or various thermochemical processes, that might not be able to behave that way.
Right, right. Really depend on the characteristics of the loads.
That's right.
Um, how do you expect Power to X to impact revenue adequacy? Could an energy-only market design theoretically see a commodity-supported price floor?
Ooh, that
Hmm.
is an interesting question. I don't know that I have an opinion about that. Uh, Look, I mean, the energy only market in ERCOT, for example, there's already a scarcity pricing mechanism. And so revenue adequacy, it just becomes a game about how much of the revenue is coming from the scarcity pricing mechanism, how much of it is coming from actual LMPs, and how much of it is coming from ancillary services. And at
Right.
equilibrium, you can design all of those things to make it to where the total revenue in the market is sufficient. It's just not what your design decisions about how those pricing mechanisms work are going to make more of the revenue come from one of them rather than another one. And the way co-optimization would work, you'd have a lot of that coming from the ancillary service demand curve, printing a high LMP and then having high ancillary service prices.
Hmm. Yep. A lot of good implications here. What about the value of adding batteries within a Power to X type scenario? Does it make sense to have some additional battery storage in some of
It probably
these
makes
configurations?
reliability sense. It's just a question of cost and how much
Uh-huh.
storage they need to have. I mean, batteries are capitally intensive things. If you have a gigawatt project, having a gigawatt battery can be expensive. Now, if it only needs to have 5 minutes of duration, then maybe it's not such a big deal. Uh, it could make it a lot more expensive and make these projects uneconomic in the first place.
Yeah. In some cases,
And
the flexibility could be, yeah.
I tend to think, the value for all of these things should kind of be inherent on their own rather than a lot of these kind of hybrid load generation projects. But from a reliability standpoint, there might be a benefit to having, more of these projects have their own storage.
Great. Yeah. There's more questions, good ones, but I'm going to have to cut it off here to recognize the top of the hour and our end of our time. So thank you very much, Andrew. This has been a great presentation, great discussion. I want to thank you for this webinar and the great insights on Power to X. As I mentioned earlier, an email will go out once the video file has been posted on YouTube, and we will answer some of these questions we didn't get to. We'll be asking Andrew if he's good enough to answer those, and post a short list of some answers to his thoughts about those as well. I'll get that posted as quickly as we can. We appreciate your engagement of those of you that attended the webinar today and look forward to seeing you again soon. As I mentioned, our fall technical workshop will be held next week in San Diego, and I hope you will join us there, as this is one of our major workshops. Further information on all the ESIG webinars and meetings can be found at our website at www.esig.energy and in our newsletter. And if you want to get in the newsletter, simply send a note to info@esig.energy and we'll get you signed up for that. So Andrew, I want to thank you again for this very timely and informative webinar. And thanks all of you for your interest today. We look forward to seeing all of you again. And in the meantime, take care and stay safe. We'll see you soon.
Thanks,
Thank
Mark.
you, Andrew.
Yep, really enjoyed it.